We will discuss a new topic today, and that is on deep neural architecture and applications. So, let us understand what is the difference between a classical neural architecture and a deep neural architecture. We have already discussed about the artificial neural network, where you can see that it is a network of different neural nodes or perceptron nodes, where you have the input at one end and it is a feed forward network. Each node takes the weighted input vector, and then the net sum of those weighted vectors are passed through a nonlinear functions, and the output is the response of that nonlinear functions, and network of all these nodes that gives you the artificial neural network. And finally, there is an input and output layers of this particular architecture. Now, the fact is that so far for classical artificial neural networks, we had only a few hidden layers. That is what we are used to do, maximum 3 layers that we could see in many of the applications, but 1 or 2 layers are more common. Whereas for deep neural architecture, you have more number of layers. You can have more than 100 hidden layers, and that is one of the major difference. So, there are different applications of this deep neural architecture. So, before describing the features of this architecture, let me give a brief overview what are the applications which are reported by this kind of architecture. So, one of the applications is an image classification, and there is a data set, ImageNet large scale visual recognition challenge data set, which was there for improving the classification algorithms for testing, and for a long time there are researchers, they are working on these data sets, and they are reporting their performance on this data set. So, in this data set you have 1000 object classes, and there are about 1.4 million images that is there in the data set, and major algorithms which have been found to provide good performances, they are deep features based, which means they have used deep neural architecture while classifying this data. So, here is a brief summary that how different kinds of what are the performances of different algorithms. As you can see that you have these traditional computer vision algorithms. So, this is a traditional algorithms, and this is a deep learning algorithms. So, all the performance indexes of these deep learning algorithms, they are very high, while the traditional algorithms, and as we are moving ahead with time. So, it is still 2015 it was shown, after that also the performance has been improved. So, this trend is increasing, and you are getting better and better deep architecture for giving this kind of good classification performance. Another kind of application that we can discuss, that is object recognition and localization. So, this is one example how this problem has been solved, what is the kind of response. You can see that in this scene the system tries to localize an object. For example, it has been shown car, and there is a pink box, rectangular box, where the car has been shown. So, this is a localization, and also it recognizes that what objects, it is a car with certain confidence level or some probability value. So, it is definitely car because it is 1.00, whereas you can see that horse is 0.993. So, there is some confusion with horse like this. And this kind of, there is also another data set where this recognition and localization tasks are performed, and you can see that using deep convolutional neural networks, we will discuss what is a convolutional neural network in this under this topic. So, they have provided, they have given better performance in this case. Object segmentation is another task. In fact, the segmentation with respect to deep neural architecture, it is called semantic segmentation, because you are not only segmenting the objects, you are also telling that what is that object. It is like localization, almost similar thing, but no, you are doing pixel level declarations that this is a segment of which type of object. So, this is one kind of application. Pose estimation is another. You can see in this diagram that poses of different persons are shown by a skeleton figure. So, skeletons are three-dimensional information, three-dimensional, it's a description of a human body, human limbs with the graphical descriptions with the 3D coordinate vertices and connected by their edges, and with our joints at different limbs. Those are representing our human skeleton. And depending upon upon the image of a person, we try to guess that what kind of skeleton configurations could provide that kind of stance or that kind of pose of a person. So, this is the estimation, and that gives you idea that in what way the person is standing or doing some activity. Another interesting application is image captioning. It's a cross-disciplinary problem. As you can see that not only understanding of images and videos, we are trying to describe using natural languages. So, you can see that with respect to different scenes, there is some language, some description, like you consider this particular image where a child, where a girl is jumping. So, it is written here, girl in pink dress is jumping in air. So, this kind of descriptions, those are generated by this kind of system. Similarly, dense image captioning, so it is further complex. So, you would like to have not only you are describing the main motto of the scene, but also you are describing every part of the image. That is a elephant, tusk of an elephant, it is a football, there is a man sitting on top of an elephant, like that. The man is wearing a red shirt. So, this kind of description and this kind of captioning could be there using this kind of architecture. Another application is super resolution. So, here you can see that examples are given. The original image is shown in the rightmost column. So, this is the original image, and this is the classical algorithm, bicubic interpolation algorithm, which produces the super resolutions or interpolated images. Whereas, using deep neural architecture, you have these middle two columns, those are the results, and you can at least see the visual quality of these two interpolated images or super resolved images. They are much better than what we have obtained by bicubic interpolation. Image art generation and transfer. This is also another very interesting applications. In fact, using deep neural architecture, you can synthesize images, you can render images. And here in particular, you can see that there is a photograph. So, this is the original photograph which is taken by a camera, and you consider the style of painters. Say this is a Van Gogh painting, and I think this is Starry Night, or that is the name. And using Van Gogh painting, so this photograph is with that style itself, painting style, this photograph has been generated. So, all these buildings etc. you can observe here, but they have very high similarity with the style with which it has been painted. And similarly, you can get the examples that same scene is rendered by different styles of painters. Many other applications are there, not only in computer vision. Deep neural architecture is used for in other areas, say machine translation and text synthesis, speech recognition and synthesis, navigating autonomous vehicles, playing different kinds of games, even playing chess, AlphaGo, these are the things. So, one of the one of the questions will come, naturally this question will arise to us, that why this architecture, why when it is giving so higher performance compared to classical techniques, but why did it take so much of time that to come to this stage? Because the concepts what you are using in deep neural computations, they are very old. They are the same neural network computation, they are the same neural network model. So, they are introduced in 80s, and their basic principles, they remain the same. So, there are two major reasons, that is why it has arrived today. It's an historical reason. That means the progress of technology and science, that is what led to every kind of new technological advancement. So, it's a new technological advancement because we have the capacity of generating large scale annotated data, and because of that availability of the data, so you can train large networks to develop any kind of model which can work in a very general, to solve any general and difficult problems. So, and then the advancement of computing power, because this training also requires high computations and it has to be done within a feasible time. So, because so there are GPU computing which has come with a which has given this advancement and which has been very much used for this kind of computations. So, availability of large scale annotated data is possible because of penetration of internet and smartphones, widespread of social networking, online shopping, etc., and advancement of computing power, as I mentioned, high throughput GPU computing, like this is one such example. Now, let us understand that what is the difference between classical image classification techniques and the deep features based classification techniques or deep neural computation based classification techniques. In classical image classification, you consider you have an image and then you would like to represent this image by some handcrafted features, which means we have studied what could be the distinct features for characterizing this image, and we develop computational algorithms to extract those features. That is what is called handcrafted features. So, it is designed by us, the algorithm is also designed accordingly, and then we extract them these features. For example, edges, shift, sharp key points, HOG, hog regional features, motion features. We have discussed some of these features in my previous lectures, and then this feature representation is input to our classification algorithm. So, you use the classifier, and there are different classifiers like Bayesian classifier, linear discriminant analysis, support vector machine, K nearest neighbor algorithms. So, different such classifiers could be there, and then we produce the output. Output is something like whether it is tiger, cat, lion. It is a standard classification problem. So, this is the classical approach. Whereas, so the problem here is that it is very tedious and costly to develop handcrafted features to handle various challenges, because there is a large variance of input image of the same object. So, this variance causes due to different kind of variations. You have viewpoint variation, deformation, occlusion, interclass variation, illumination, clutter, instances, scale. Some nice examples are shown here with respect to that tiger. Say you can see one by one that what kind of variations are there, and so that is why this is very difficult to develop a very general algorithm. It is dependent on one application and it is not easily transferable to other applications. In deep feature based algorithm, we learn the feature representation first using the it is a automated learning, it is unsupervised learning. So, your mechanism is such that they extract the features depending upon the problem statement, depending upon the applications. So, here usually it has been shown, we will discuss that part, that how you are learning even the feature extractions, and that is not handcrafted. Your neural network itself is learning to represent the features. So, there are different levels of features representations when you are doing deep feature representation. So, you will have low level features, and as you increase the level of abstraction, you can have mid level features, you can have high level features, and then you train the classifier using these features. The whole thing you are doing in one shot. That means it is augmented, it is coupled. In the previous case, classification scheme is independent of feature representation scheme, but now feature representation and classification, they go hand in hand, they go in one shot, and then you get the output. So, it utilizes large amount of training data to learn features, and it has rich hierarchical representations, as I have mentioned, that from low level, mid level to high level feature representation. So, multiple stages of feature learning processes involved, and it learns features adaptively. So, in the context of your application, these features are learned. Mostly you will be considering supervised learning and in the deep neural architecture, particularly the classification problem, as we have discussed, that you have the training samples, you are training the network, and then you are classifying. So, this is an ideal supervised classification setup, and we call it also supervised learning. So, the problem here is that you have X data and Y level. So, I am just revisiting this, we have discussed also in the context of classification previously. So, X is the data, Y is the level, and our goal is to learn a function f which will map the data to the level. And different kinds of problems like classification, regression, object detection, semantic segmentation, image captioning, all could be mapped to this kind of learning framework. So, let us consider image classification, and in the image classification, the problem is that what class that image belongs to and how to classify. We have already understood this problem statement. So, in this case, we would like to learn a parametric function f, which composed by weight parameters of the model to classify image x as class level y. So, it is a data driven approach to learn the model in 3 steps. First, you have to define the model, like we have defined the prediction of class y given the input and the model w. So, artificial neural network we discussed, that is one example of model, and as I mentioned that deep neural architecture is nothing but the same artificial neural network model, only you have more number of hidden layers. So, you have input data as image pixels here, and you have the model weights, and this is a model structure, and you have to, this is a predicted output or image level. So, first step is define model, next step is you have to collect data. So, this is for the supervised learning, it is important that you should have annotated data. Xi is the instance and yi is the level of that data. So, this is the training input and this is the true output yi, and then you learn the model. So, here we consider that there is some mapping function that you have to learn, and how good is that mapping function and what is the gap, then we try to update that gap. So, in terms of weights, so whatever weights are there, what is the performance? If the loss is more, then we need to update, so that loss should be minimized or loss should be reduced. So, we use a loss function here to judge to assess the performance of a model. So, which is represented here by this notation. So, this is a loss function. What is the predicted output and what is the ground truth, depending upon this loss function is defined, and for a set of training samples you accumulate these loss functions, and this is a regularization term because your model should not be too complex. We will discuss this part also. So, let us see. So, this is predicted output and this is a loss function, and we would like to minimize the average loss over training set, and this is called regularizer or which penalizes the complex models, and this is learned weights. So, total loss can be considered as the data loss and the regularization loss. So, data loss is given by the functions L here, that is a data loss, and regularization loss is given by RW. So, a loss function tells how good is the current classifier, and data loss is the model prediction should match training data. So, what is the deviation? So, there are different kinds of examples of data loss functions, like in multi-class support vector machine we can use hinge loss. Here now we can see that each wrongly classified sample produces a loss. So, it is the difference of the functional values of the predicted sample, predicted functional value, predicted sample, and the model sample. So you can see that functional form here in this case, and the softmax loss or multinomial logistic regression loss, that is given in this form. So in this function, we are estimating the probability of a level, true level, given the input data. So if this probability is very high, then this loss will be less. So using this negative sample, we make it a positive function. Sometimes this probability is computed with respect to the responses of all other classes. So you know, in the output layer, say if you have in the output layer say n classes, and the response is provided by say S y I of the ith class, then we consider that say y I is a true class. So we consider the S y I of the true response of the true class. Now the probability of that class is given by this expression. This is a softmax expression. You raise it to the exponentiation and normalize it by the sum of all these exponentiations. So that would give you the probability value, and it is actually modeling this particular term itself. It is giving this probability of y given data. This is posterior model. So cross entropy loss is also another form of softmax loss. When you have two class entropy, then you have either say class 1 or class 2, that means object class and background class, for example. And if the probability of the object class is p, then non-object class is 1 minus p. And as you can see, it is just generalization. So when your object class y is 1, level is 1, then you are only considering if it is predicted as y, then you are considering the when the object is true class of the object is true class of the sample is the object, then you are using log p. Otherwise, you are using log 1 minus p. In the multi-class, you are extending this particular computations with this expression, where you can see that YOC is a binary indicator. It is 1 if the object belongs to class C, and we are considering only probability of that class for the kind of sample. Here O is the input sample. So estimating probability of O belonging to class C. In a more general framework, you may have a distribution of probability distribution of the true class also. So it is not binary always. So it is true probability of O belonging to C. Use this, you can use it for the cross entropy loss. So in the regularization loss, we would like to have the model simple, and there we would like to have the W, the size of the W as small as possible, and it is not an unique with the data loss. See, there are different kinds of regularization function which tries to put a constraint on the values of W. For example, you would like to minimize the square of the magnitude of W, sum of the square of the magnitude of W, that is L2 regularization, or we can use L1 regularization instead of square, we can use absolute values. You can have a linear combination of these two, which is an elastic net regularization. So finally, for the training, we would like to solve this problem, optimization problem. So given this loss function, which has given this objective function which has data loss term and regularization loss term, and then we would like to minimize with respect to a chosen weight. So what is the best weight which can minimize it? So this is GW is the sum of these losses, and we would like to minimize GW. So what we could have done, that we can use random search. That means once again we need to choose some initial guess of W and or pick here and there and try to see what kind of loss you are getting and try to get the minimum out of them, but it is very inefficient. So, standard algorithm would be gradient descent, again the same backpropagation algorithm what we can use it here. So, gradient descent algorithm we have discussed earlier. Let us revisit once again in the context of this particular topic. So, we can initialize W randomly and then we can go ahead computing the gradient of that W at the current point. So, which is expressed as this grad of G W, and then move downhill a little bit, because that is the updation process. So, you move along the in the opposite to the steepest increase of the gradient. So, which means steepest descent of the gradient value. So, minus alpha into grad G W, alpha is a learning factor here. So, this is updating the weights at each iteration, and this is a learning rate, alpha is a learning rate, how big each step should be, that needs to be decided. And backpropagation algorithm also we discussed that it has two passes, one is forward pass, another is backward pass. In the forward pass we run the graph forward to compute loss, and the backward pass we run the graph backward to compute gradients with respect to loss. And we know that it is efficient to compute gradients for big complex models. So, supervised learning could be also considered as a linear regression problem, where your input is a vector and output is also a vector. So, in a linear regression, one of the linear regression problem is that the model is linear. So, the if your input is x, then use the weight linear combination of input, that is W x. It is not linear, not only linear combination, you multiply with any matrix W, that would give you another vector, and that is a linear model here. So, W dimension of W should be d out into d in, because your output vector is of size d out. So, it is just a matrix multiplication, that is the model here, and you can use the Euclidean distance as a loss, norm of the deviations. So, your learning problem here is a linear regression learning problem, and coupled with regularization, the corresponding objective function has been shown here. And regularizer is using Frobenius norm of matrix or sum of square of these entries. And supervised learning, you can use the neural network, where you can consider it's a sequence of linear layers. So, it is a new model. Once again, as you can see that your learning problem is almost remaining same, because what you are doing, if you are using multi-layer neural network, so first layer W1, since this is linear, next layer also you can multiply with W2, but this W2 W1 can be combined as a single matrix W. So, it remains the same learning problem. So, even if you increase the layer, finally it is not increasing the capacity of problem solving, it remains the same, power of your problem solving remains the same. So, by introducing nonlinearity here, you are giving another complexity to your model and increases the power of solving this problem. So, let me take a break here, and we will continue this topic in the next lecture. Thank you very much for listening this lecture.